Hey guys, Dr. J here, and in this video, we're going to talk about how to calculate a weighted average. And we'll do this using the gravity data that we acquired in class. So this is gravity data that was acquired using a Sintrex CG5 gravimeter, and you can see the values here. Remember, the Sintrex CG5 is a relative gravimeter, and so these are not the value of absolute gravity at these locations. These are just the relative values of gravity that were collected during the survey. And so what we'll need to do eventually is subtract out the value of our reference station, which in this case is station 1. And you can see we've got two measurements of station 1, and that's so that we can calculate a drift correction if needed. And so what we want to do now is each time the gravimeter measures gravity, it's going to take 4 separate measurements. And you can see this here as gravity 1, gravity 2, gravity 3, and gravity 4. So our station number is here, and then each one of these gravity columns is a measurement that was made by the gravimeter at that particular station during one data occupation. And then with each measurement is also a standard deviation. So this standard deviation is given by the instrument. And so what we want to do is to calculate a weighted average gravity value for each station so that each station will have a single gravity value which takes into account all of this data, but also takes into account the standard deviation here. So we could just calculate a basic average, right? And of course, the basic average would just be the sum of this plus the sum of this plus, sorry, I'm saying this a little wrong, but it's the sum of the 4 measurements, except I don't want the sum. I want actually the sum divided by 4. And so there would be my average gravity values for each site. However, you'll notice that the standard deviations here can be a little bit different for each measurement. So in some cases, they're a little bit higher, and in some cases, they're a little bit lower. Now, the standard deviation, you can think about this as kind of a measure of the uncertainty or the error in the measurement. And so this first gravity measurement is going to be 6273.729 plus or minus 0.014. So this is like an uncertainty in our gravity measurement. And the idea here is that measurements that are less uncertain or more certain, we want to weight those slightly more. And measurements that are more uncertain, we want to weight those slightly less in our average. And so instead of just doing a normal weighted average, we're going to calculate instead of calculating a normal average, we're going to calculate a weighted average. So this is actually just the average. And now what we want to do is figure out how to calculate a weighted average where we account for these standard deviations here. All right, so X here, this is just our measurement, our observations, the data. Whoops. So those are our data points. And then this Greek letter sigma here, this is the capital Greek letter sigma, that just means the summation or the sum. We're going to sum from I equals 1 to n. So basically just we're going to sum up all of our measurements and then divide by the number of measurements that we have, 1 over n. So this is our basic average. We sum the measurements, we divide by the number of measurements, we get our regular unweighted average. Now we want to calculate the weighted average. And how we're going to do this is we're going to start by moving this n inside the summation. So I'm not going to go into the proof right now, but we can basically write a regular average as the sum from I equals 1 to n of xi over n. And really I should take away this weighted part here. So this is just our regular average still, but we've just moved the 1 over n inside. And so what this means is that if we have our measurements, we divide each measurement by the number of measurements, and then we sum those quantities up, that will still give us our same unweighted average. And we can write this in a slightly different way. I equals 1 to n, 1 over n, xi. And this we can write sum I equals 1 to n, wi xi. Okay, so what have we done here? What we've done is our normal average, and let me just say down here, wi is equal to 1 over n. So now all these equalities hold. So our normal average is the sum of all the measurements divided by n, and we just sum those up. And again, this works because this 1 over n is a constant and can go inside the summation sign. So we can write the sum this way. This is still the same thing as the top equation. And now we can write this as 1 over n times xi. And now we can write this as a weight, wi times xi. So this is basically the weight on each measurement times each measurement, summing them up. And so this whole thing is exactly the same thing as long as we set our wi, our weights for each observation, to be 1 over n. So a regular average is just simply a weighted average, where the weights are all the same and they're equal to 1 over the number of measurements. That's what a regular average is. And so you can imagine now what we can do is we can change these wi. We can change the weights to be whatever we want as long as they meet certain criteria. So for this to be an average, we need to have the sum of the weights, I equals 1 to n. So again, this is just the symbol for sum. So w1 plus w2 plus w3 all the way up to wn. The sum from I equals 1 to n of wi, we need those to equal 1. And that is for this to be a proper average. So now let's jump back over to the data and think about what these weights should be. All right, so here we are back in our data, and we've got our standard deviations here. We want to weight the values of gravity that have a lower standard deviation more, right? So if the standard deviation is lower, that means lower uncertainty, lower error. So we want to use that measurement more. So for our weighted average, we could imagine using wi is equal to 1 over sigma I. And sigma here is just the Greek letter sigma, which is used for the standard deviation. So sigma is a way of putting in, of symbolizing the standard deviation. So I'm going to say my weights are 1 over sigma I. Well, that's great, except there's a little problem, which is that my weights, in this case, will not add up to 1. So if I take 1 over the standard deviation, 1 over the standard deviation, 1 over the standard, you can see these are very small values, and then you take the inverse, and then you add them up. That's definitely not going to be 1. So we need to do something to make these standard deviations be 1. And so what we're going to do is we're going to actually take our weights as 1 over sigma I, but then we're going to adjust those weights. And so the way that this is going to work is we'll say our, maybe our wi, you can call it prime, is going to equal 1 over sigma I. And then our wi is going to equal wi prime divided by the sum of all wi primes. All right, there we go. So here's my wi prime. And so what I've done here is just divide each one of my 1 over sigma i's by the sum of all the initial weights so that these weights now will equal to 1. So what I'm going to do is I'm going to rewrite this Excel sheet now and copy and paste these gravity values. So this is just gravity 1 values. And then I'm going to have the standard deviation for the gravity 1 values. So I'm just going to copy those into here. And again, I'm sort of doing this the slow way because just for demonstration purposes, but there are certainly faster ways to do this using Python or using other things. But here's the easy way. All right, so I've got my gravity values, my 4 gravity values for station 1 and my 4 standard deviations for station 1. I'm going to just take 1 over, well, I'm going to calculate wi prime is equal to 1 over sigma I. So I'm just going to say that this is equal to the value, not the value by itself, but 1 over the value. And I'll go ahead and take that suggested infill. All right, so now I've got my wi primes, and I need to calculate now my wi's. Well, in order to get that, I need the sum. So we're going to say I'm going to take the sum of all my weights. There we go. There's the sum. And now I want my wi's. So no longer wi prime, but actually wi. So that's just going to be equal to the wi prime divided by the sum. And we'll go ahead and bring that down. Whoops. And because I'm dividing, in this case, by the same sum, what I need to do is add the $sign in here for this equation. That'll allow me to get the right equation there. Very good. Okay. Then we get weights that add up to 1. So now these are my actual wi's. Now the next thing I need to do is multiply each weight Remember in my equation, here, each weight gets multiplied by the value. Now, in this case, the weights we talked about were 1 over n. So that's our regular average. In this case, our weights are not exactly 1 over n. So 1 over n in this case would be 0.25. And you can see some of the weights are less than 0.25. That's these two. Some of the weights are more than 0.25. And if we compare, we can actually see, in this case, the standard deviations go from small at the top to large at the bottom, and the weights go from large at the top to small at the bottom. And so it's exactly what we want. We want to have slightly more weight on the standard deviations that are a little bit lower and slightly less weight on the standard deviations that are a little bit higher, or I should say on the observations that have standard deviations a little higher. We're going to take each weight and multiply it by each gravity value. And we don't need this one here. So now these are our weights times our values. That's this quantity right here. So now we've got the weights, and in order to get our actual now weighted average, we're going to sum these up. And so now what we want is we're just going to say sum of those 4 values. And this now is our weighted gravity average. And so I'm going to copy this, put it up here for station 1. Oh, and I'm going to paste values only. So that's how I can calculate a weighted average for each one of my gravity measurements. Now, in this case, it's gravity data, but you could do this with really any type of data which has an uncertainty on it or some kind of information that would let you tell which ones are better quality data or worse quality data. You can do this same kind of process with that.